853. Video for 853.
Hello everyone, my name is Russell Paulette and today I'm going to talk to you about our work on practical anonymous subscription with revocation based on broadcast encryption. This work is with fellow authors Xunyi, Elisa Bettino and Fangyu Rao. The general format of this talk will begin with introduction. This will be followed by previous work and some motivation. Then we'll discuss some background, which will lead into our anonymous subscription protocol, which will include the model, the basic construction, and the extended construction. We'll perform some protocol analysis in terms of security and performance. And finally, we'll conclude the main ideas of this talk. So we consider a scenario where a client wants to subscribe to a product or service provided by a server, but also wants to maintain their anonymity during usage, such that individual user behavior is protected from data mining efforts. At the same time, the server wants to ensure that only legitimate users of the subscription are active, and at the same time be able to revoke users who fail to pay the subscription fees on time. We consider a concrete example of an online research journal, where the online research journal may want to understand individual browsing habits to learn what users are interested in. So the general model is we consider that the user first registers with a service and then at a later time logs into the service, but the server does not know which particular user is using the service. That's shown on the diagrams on the right on this slide. Previous solutions for this problem are typically based on some combination of blind signature and zero knowledge proof. Briefly, blind signature is a digital signature where the signer doesn't know which message has been signed, whereas zero knowledge proof allows the prover to prove a statement about a secret to a verifier without disclosing the secret. The basic steps of a blind signature are as follows. The client first sends a blinded version of some message M prime to the server, which the server responds with a signature on M prime as sigma prime, which is sent to the client, who is able to determine sigma from sigma prime. Then at some later time, the client shows M and sigma to the server, and the server can verify sigma is that as valid signature on M, but the server does not know which message was originally signed by the server, so is unable to determine the actual user from the signature and message alone. But this requires that the storage of all previously used tokens to prevent double usage, which is expensive for our subscription application that may have many users. The basic steps for a zero knowledge proof are as follows. Upon registration, the server sends a secret value to the client. Based on this secret value, the client generates a proof such that they know the secret, SK1, SKI, and the proof is sent to the server, but the server is unable to learn which secret value the client has knowledge about, but is convinced that they do have knowledge about it. But by their very nature, the zero knowledge proofs are computationally expensive, and generating such proofs will become a bottleneck for the subscription application. So we want to improve upon the following issues of previous systems that aim to facilitate anonymous subscription, which include poor performance, key sharing issues, and the absence of revocation capabilities, where both blind signature and zero knowledge proof don't directly support client revocation. That is, revoking a client before the expiry of the secret value. Before we look at our anonymous subscription solution, we need to introduce some background, which includes the bilinear map and broadcast encryption. So we consider that we define a bilinear map in the following way, where we have two groups G1 and G2 with associated generators G1 and G2. And we define a map such that it is linear in both the first input and the second input, which effectively means that we're able to multiply in the exponent. If we also have the G1 equal to G2, then we consider it to be a symmetric bilinear map, and we only consider symmetric bilinear maps in this work for simplicity. We now recall the special case of Bilinears et al.'s broadcast encryption scheme. The scheme is given by 3 algorithms as follows, where n is the number of clients. So basically it computes gi as g to the power z to the power I for some integer z, and publishes all this information, including v, which is g to the power gamma, and the private key for each client is gi to the power gamma, and we observe that di is also equal to v to the power z to the power I. We encrypt by choosing a random t, and we compute k as given by the formula. And then we set the ciphertext as a pair of elements in G, and then we output the ciphertext C and K, and then we can decrypt, and which effectively works only if we have if one of the private keys was included in the encryption process, and if it was not included in the encryption process, then it fails to recover K from the ciphertext C. But observe that the private key is 1 group element in G, while the ciphertext is 2 group elements in G. So for our anonymous subscription protocol, we consider the interaction of the following 3 parties. For some issuer I that is responsible for controlling access to the subscription service, a service provider that facilitates the operation of the subscription service, and client C who wants to access the subscription. Our basic idea is that we use broadcast encryption to share a secret with a set of eligible users S, and when we want to revoke, we just exclude the certain users from that set. And in a bit more detail, this described by 3 randomized algorithms as follows. This issuer generates the public and private keys. The client registers to receive a particular private key and secret key from the issuer, and then during the login phase, the client sends a request to the service provider, which broadcasts a secret to all eligible clients, and effectively, if the client is able to decrypt the secret, they can show the secret to the service provider to prove that they're eligible to use the subscription service. We consider 2 main security issues in our model, where client anonymity, where the service provider acts as the adversary and tries to identify a client CI, and authentication, where the adversary tries to authenticate themselves, which results in a session key without any valid key distributed during setup. So we now present the basic construction of our protocol as follows, which effectively creates an instance of the Bilinear et al.'s broadcast encryption scheme, and in addition creates a key pair for a digital signature scheme with signing key SK and public key PK. And when the client wants to register, they distributed a private key and for their particular case, and the signing key, which is stored in a tamper resistance device. And note that the tamper resistance device prevents the sharing of the private key with others. So when the client wants to log into the server with the tamper resistance device, the client and the server engage in the following 5-step protocol. The client C randomly chooses A and X and computes the A and R as given by the formulae, and sends this AR to the service provider. Upon receiving this message, the server computes the following values, where C0 and Z1 is the broadcast encryption of the ciphertext, which is and EGN and GI1 to the power G is the corresponding key. Next, the server signs the signature on all these values and sends to the client, and sends all of these values to the client. And upon receiving the message from the server, the client verifies the signature as being true, and if true, it computes that the product was computed correctly. and inputs the this product and the signature into the tamper resistance device, which computes Q, which is passed back to the client that computes the pass as P, and then the session key is computed as T to the power X, which is equivalent to EGGYX. Finally, it sends the pass to the server, and the server checks whether or not the pass is correct by comparing it with B, and if the check was successful, the server computes the session key as R to the power Y, which is EGXY, which is the same as key derived by the client. And note that each session can be uniquely determined by the server on the server by C0. And when these when the server session concludes, the server S removes the session from the list of active sessions and computes the signature on C0 and sends it to the client. And then upon receiving the signature, it inputs it into the tamper resistance device, which terminates the session and resets the tamper resistance device to be ready to compute another queue. In our basic construction, the public key and private key is given as follows. This means in our basic construction, we can only support a maximum of n users, but we can overcome this limitation by introducing, instead of one value for gamma, but many. This makes the SKBG sub alpha to the power gamma sub beta for alpha from 1 to n and beta from 1 to m. This effectively allows us to reuse the public key without reset up. Our solution addresses the security problems we outlined in the system model, where the client's login request is of the form AR for some A and X, but the server is unable to distinguish this from a random element in GT. And without a valid private key, the client is unable to prove its eligibility because they're unable to distinguish it from a valid session key from a random element in GT. And this shows that we also have authentication security. We can compare our protocol with similar protocol, and we find that in general our protocol is more efficient, and this is due to the efficiency of the broadcast encryption scheme, which we also demonstrate the efficiency empirically and show its performance as the number of clients grows, and also compare the implementation of our protocol with other similar protocol. So we presented an anonymous subscription protocol, demonstrated it was secure against standard attacks, and we showed that our protocol was practical through empirical evaluation. Thank you.
Are there any questions? By the way, this is Murat again, I don't know whether you can see me. I made a mistake with respect to introduction because the notes were slightly changed later on. As you noticed, the talk is given by Dr. Russell Pollard, who is a current research fellow with the Computer Science and Software Engineering at RMIT, University of Australia. So sorry for this mistake on the introducing the presenter. Do we have any questions about this technique? I don't know whether Russell is online with us, or maybe someone else from the group is online. Are there any questions? Okay, so if not, we'll move into the second talk of the session. The second talk is paper, just a sec, paper 606, SVkNN. Please just give me a sec. SVkNN, efficient, secure, and verifiable k-nearest neighbor query on cloud platform. It will be presented by Ninging Kui, and we don't have any further information about the presenter, so we'll now go with paper 606. Please.
Good afternoon, everyone. My name is Ningning Cui. I'm come from Northeastern University. The title of my presentation today is Efficient, Secure, and Verifiable Key Nearest Neighbor Query on the Cloud Platform. As we know, the outsourcing model is the most popular in the cloud environment. Under this model, it mainly involves three entities: the data owner, the user, and the cloud server. The data owner outsources their data to the cloud, and the cloud server, rather than the data owner, provides the searching service for the user. In our paper, we studied the secure and verifiable k-nearest neighbor query. As shown in the figure, there exist 8 objects. When k is true, it is to retrieve the top 2 objects owing the shortest distance with the query, that is P1 and P6. However, under this outsourcing model, without privacy-preserving scheme, the cloud server may reveal sensitive information, and without the verification scheme, the cloud server may return the tampered point or incorrect point. The framework used in our paper is shown in the figure. The input is encrypted data, the secure index, and the encrypted query, which are generated by the data owner. The outputs are the objects matching the query conditions, which is implemented by the cloud server. Compared with the traditional outsourcing model, we adopt to include resistant clouds to perform the following secure protocols. In addition to support verification scheme, we also modify this framework by adding the signature function and the verification objects. The goal of our work is to protect the privacy of the data, the query, the result, and the access pattern, and meanwhile guarantee the correctness and the completeness of the results. There exists a lot of works to address the related problem. However, no existing work can deal with our problem completely. And the challenge of this problem are how to design a unified structure for the secure k-nearest neighbor query while guaranteeing the results integrity, and how to verify the integrity of the results while the user does not know the real points information except the results, and how to accelerate the efficiency further. Here are some preliminaries used in our paper. We use parallel homomorphic as encryption scheme, which is homomorphic addition. We use cryptographic hash as signature scheme, and we use the data packing to improve the efficiency. This is the view of our solution for the problem. Intuitively, we adopt Vinoy to integrate the index and the verification information together and into a unified structure. Further, to guarantee secure operation on the index, we design a series of secure protocols to realize this goal. Specifically, to support SVkNN, we propose a novel data structure named Secure and Verifiable Index. It consists of 2 components. One is encrypted partitioned grid, and the other is bucket-based encrypted Vinoy diagram. For encrypted partitioned grid, as shown in the figure, the space is first divided into n disjoint convex polygonal regions and then we partition the diagram into m multiply m grids averagely. For each grid, we record the ID and its spatial coordinate of the overlapped Vinoy cells. The goal is to check which Vinoy cell the query locates in without leaking the privacy. That is, finding which point is closest to the query. Next, for the bucket-based encrypted Vinoy diagram, as shown in the figure, the data owner uniformly partitions the entire table into buckets, each of which contains W records. In the first column, it pegs the ID and the spatial coordinate of each point separately. In the second column, it pegs the Vinoy cell of neighbors of each point and stores its hash value. To avoid the inference attack, we paired some dummy records to guarantee the identical size. In the final column, it stores the encrypted signature of each point. Moreover, the neighbor's hash value and the signature can be computed as follows. And the goal is to support fast k-nearest neighbor query processing without leaking the privacy. That is finding k-nearest neighbor points and guaranteeing verification information. And based on VSI, the first task is to read the objective grade contain the query from encrypted graph privately. And the first step is to locate the position of object grade in encrypted G. Here, we propose secure division computation protocol. As shown in the figure, giving Q and the grade-wise data, SDC protocol is used to compute the quotient in a secure manner. Here, we construct the equation to compute the quotient securely. And based on the computed grade coordinates, we can locate the object grade quickly. Next, we propose secure grade computation protocol to read the content. The main idea is to leverage a vector to indicate the position in EG. Here, we adopt obfuscation and permutation schemes to avoid access pattern privacy. Obfuscation means adding random numbers to the elements in vector, and the permutation means randomly changing the order of the elements in vector. After SGC protocol, we can get candidate point set. Further, we can get corresponding distance set. The important step is to determine which distance D is the minimum. Here, we propose a novel secure minimum computation protocol to achieve this. Giving the encrypted distance D0 and ID0 and the encrypted D1 ID1, FMC protocol returns the minimum of the distance and the ID. And note that our FMC protocols just need 5 times encryption and 1 time decryption. In addition, it avoids an extra process of computing the minimum of the ID. Based on MSC protocol, we can get the point ID of the minimum distance. Secure cell read protocol aims to read the row matching the computed ID from the bucket further. Similar to SGC protocol, we adopt obfuscation and permutation scheme to avoid access pattern privacy. As shown in the figure, after SCR protocol, we add the neighbor points into the candidate set for the nearest neighbor computation. SCR does not need to check all records and just needs the secure root of n times decryption averagely. For the query processing, repeat the above protocols until the result set is K. Note that this inserted neighbor points may contain the redundant points which have been the result already. Here, we eliminate the redundant points at following 2 scenarios. One is eliminating the current nearest point from the candidate set, and the other is eliminating the point in result set from the neighbors of the current point. In addition, we generate the verification object during the query processing based on a transformation vector V. And note that the transformation won't affect the distance and can guarantee the data privacy. And after that, all transformed points, the transformed queries, the hash value of the result points neighbors, and a signature of result points are inserted into verification object. At last, the cloud server returns the results and the verification object to the user. The user now has the verification object and the result. For verification process, it involves 2 parts. The one is correctness. Correctness means the points in result set are all belonging to the original database. Here, we adopt the hash signature to achieve this. If the new computed signature matches the signature from the verification object, we say the correctness is satisfied. The other is completeness. Completeness means the points in result set are the real k-nearest neighbors. Here we adopt the distance comparison scheme. If the 2 following If the following two conditions are satisfied, we say the completeness is satisfied. Is VSI structure efficient enough for SVkNN? We find that during the query process, it involves many encryption operations for random numbers. We observe that homomorphic multiplication operation is rather superior to encryption or decryption operation. To alleviate the latency, we propose to optimize the schemes. The one is homomorphic-based random number generation. We first generate the encrypted one, then compute the encrypted random number R as encrypted 1 to the power of R. The other is pore-based random number generation. We generate two pores in advance, denoted as R and ER, where R stores the random numbers in the form of the plain text, and the ER stores the random number in the form of the ciphertext corresponding to R. We first randomly chooses the needed random numbers from R and then picks their corresponding encrypted form from ER. Now I will introduce our experiment. In experiments, we use two data sets, including a real data set and a synthetic data set. And the details are shown in the table. The red value is the default value. In addition, we compare with other related algorithms and test the performance of our algorithms. We first compare secure minimum cooperation algorithm with others. Note that our algorithm outperforms both of them, especially our algorithm are at least 5 times faster than SMC and about 100 times faster than SMN respectively. Next, we compare the k-nearest neighbor computation with others under diverse parameters. Note that our algorithms are also outperform both of them, especially with varying number of points. When n is 10,000, our algorithm are about 20 times faster than SVkNN and about 60 times faster than SVkNB respectively. And with varying query k, when k is 20, our algorithms are about 50 times faster than SVkNN and about 100 times faster than SVkNB respectively. The last is with very key size. When k is 1024, our algorithms are about 30 times faster than SVkNN and 70 times faster than SVkNB respectively. And last, we compare our algorithms as expected. The improved algorithms significantly outperform the basic one when varying packing size and grid size. Throughout this paper, we investigate and propose the secure and verifiable k-nearest neighbor query. And we first proposed a verifiable and secure index to support fast search and verification. After that, we designed a series of normal secure protocols and compact verification strategy to facilitate the operation over VSI. And last, we conduct extensive experiments on real and synthetic data sets. Thank you very much. Any questions?
Yes. Let me, Ning, you go. Basically, Shantanu had questions. Shantanu, maybe you can unmute yourself since we are in a small group. I think it should be okay. Yeah, go ahead, Shantanu, ask your question, please.
Hi, thanks for the talk. I want to ask you your question. So first thing, you told that in your approach, you are hiding the size of the bucket by adding fake rows. So how many fake rows you are adding in each bucket? And is there any that you cannot add X number of more than X number of rows in each bucket?
Yeah, I answer the first question. The fake rows depending on the maximum number of the partitioned grid. The fake number is depend on the maximum number of the partition grid. I add the figures in to the identical size, you know. So the difference is the of the maximum minus the number of the grid it contains.
Maximum in one of the grid minus the current. Okay, I got it. Thank you.
Yeah. Okay.
Yeah, thank you. And the second question is, so when you are outsourcing the data, are you outsourcing the live data, or you just first collect the entire data and then outsource?
In our experiment, the data is generated by real data and synthetic data. The real data is published in the web, and I think it received from the GPS, but it is the static data set. It's not the live data set, you know.
So if the data is live data, then how we can add fake rows? Because in that case, I don't know the maximum number of tuples in any of the grid.
Yeah, because the index is generated by the data owner in advance, so it's not the live data, and it's just it's not generated by now. It's it's not the live data. It's the static data.
Okay. And third question is regarding axis pattern attack. So you told that your approach hides axis pattern. So is this based on the secure multi-party computation concept? That's why it is hiding axis pattern, or something different?
Yeah. In our work, our work preserves the access pattern. It means the cloud server does not know the real ID of the data in the original database. Yeah, our work protects the type of the privacy.
Okay. And the last question is on slide number 16. You showed that the user will get some redundant values. So
this process is done by the cloud server during the query process. It means the generate verification object during the query process. So the cloud server do this process.
So user is not doing the redundant tuple elimination. Cloud is doing.
No, not the user or data owner. This process is implemented by the cloud server.
But then cloud server will not know, okay, these are the redundant tuples. Will it not lead to some security violation that I am eliminating some?
Because this process is implemented in the form of the SFour test, and it won't review the privacy of the data or something else.
Okay. Thank you very much.
Okay, thank you very much for your question.
If there are not any other questions, I don't see anyone on the chat or live. Let's thank the speaker again, virtually, I guess. I'll do that. So we go to the next talk, which is 656, which is an anomaly detection system for protection of relational database systems against data leakage by application programs. It will be presented by Darren Fadol Al-Karim. She is pursuing her PhD degree at the Department of Computer Science at Purdue University, and her main research interests are on data protection from insider threat and software security. So, Aparna, please play the 656.
It is difficult to avoid the stories in the news about data breach and data leakage. Data leakage has been one of the top 5 attack vectors in 2017 and 18, and one of the main causes of such leakage is careless or malicious insiders. According to the IBM's Cost of a Data Breach report, the average total cost of a data breach is in 2019 was $3.92 million, and in the US it was over $8 million. Data is the most valuable asset to businesses, especially when the data is related to customers and payments. Data leakage can affect an organization's reputation for years, and database systems are widely used as data repositories. So, securing databases from malicious outsiders and insiders who have privileges to access them is critical. One possible source of attacks to databases is application programs, as attackers might exploit vulnerabilities in a privileged database application. They can perform code injection or code reuse attacks to steal data. Such attacks usually result in changes in the program's behavior, and hence program monitoring techniques represent an effective defense to detect ongoing attacks. One of these techniques is anomaly detection systems. Many approaches have been proposed to detect anomalies in database queries or application programs. However, they suffer from at least one of the following limitations. Inability to monitor data in use, or inability to link activities to data sources, or inability to track users or applications' actions on data after gaining access to the data, or inability to track sequences of actions on data. In this project, we address the following problem. What happens after an application program retrieves some data from the database? Is it possible to detect abnormal activities that could be a sign of data leakage attempt? The design of such an anomaly detection system is challenging, as it needs to fulfill the following requirements. It should require the least possible modifications to the code. It should not introduce high overhead, and it should have high accuracy. We address these challenges by designing and implementing AD-BOM. It's a system to monitor data in use with the goal of detecting data leakage attempts by application programs. We aim at monitoring data whose source is a relational database. We call it the targeted data. The system mainly considers the attempts that result in changes to the library and system call sequences that the application issues while it's running. Our system works in two phases: detection phase, training phase, and detection phase. In the training phase, the system collects normal traces, program traces, and builds a profile of the program. And in the detection phase, the system uses the profile to monitor the use of the targeted data by the program at runtime. The main contributions in our system are its ability to link activities performed by application programs on the data to its source, which is the database. It analyzes both content and context of the data to detect data leakage attempts. It applies a hidden Markov technique in a new way to achieve high detection accuracy. It integrates static and dynamic analysis, the ability to predict new activities that may be a sign of data leakage. There are different methods that enable the attacker to change an application program. The first one is having direct access to the code. For example, if the attacker is a developer, he can modify the application code to steal data by increasing query selectivity or adding new commands. Another way to change the application is having access to the application's binary. The attacker can perform code injection or return-oriented programming attack. Another way is program vulnerabilities. They enable the attacker to change the program's behavior without having access neither to the source code nor to the binary. The program if, for example, doesn't use prepared statement to submit queries, then the attacker can perform SQL injection attack. Or if it doesn't use encrypted connection, then the attacker can perform man-in-the-middle attack. Now I'll briefly explain the phases of the system, discuss the experiment's results, and outline our plans for future work. In the training phase, AD-PROM statically analyzes the application binaries and extracts the control flow graph for each function and finds the data dependency between the statements that transfer the targeted data, which is data from the database, to the program, and output statements like the library called printf or the system called write. After that, AD-PROM for each function will approximate the conditional probability for each pair of adjacent nodes, compute the reachability probability for each node in each control flow graph. It then computes the transition probability for each call pair to build a call transition matrix. The system then aggregates all functions, call transition matrices into one matrix that represents the whole program. We can see here in this example, finding the data dependency enables the system to label this print statement, and also the system records the block number to distinguish between this command and the other one, so to distinguish between different paths in the system. This is a small example of a call transition matrix for this function. As we said, it will compute the transition, the transition between each pair of calls. Okay, if the number of the calls in the program is small, the system then initializes the transition probabilities matrix of the hidden markup model using the program call transition matrix and map each call to a state. However, if the number of the calls in the program is big, the system will first reduce the program call transition matrix using BCA. BCA is a dimension reduction tool to reduce a large matrix while preserving most of the information in the original data, and then the system will use k-means clustering to map more than one call to a state in the hidden markup model, and then it will use the cluster result to initialize the model. The system then instruments the program dynamically while running the test cases to collect call sequences and then use the traces that were collected to train the model. In the detection phase, the system instruments the monitored program application to track data dependency and collects the library calls that the application program issues at runtime. Then n-length sequences are sent to the model. The system will compute the probability of each sequence and decide if it's normal and or not normal and report the result. Okay, this example shows how labeling output commands that has data from the database and recording block IDs enable the system to detect changes in the code, in the code. In the figure, we can see at line 4, the program prints data retrieved from the database. The attacker could modify the code by adding new commands like the ones in line 5 and 6. Executing the new commands will issue a call sequence similar to the original. However, recording the block IDs where the original print call is supposed to be called helps the system to recognize the difference between line 4 and 6. Okay, in the experiments, we used 2 data sets to evaluate AD-PROM. The first one consists of 3 client applications. The other dataset consists of 4 of the application programs provided by the software artifact and infrastructure repository. We use this dataset to test the analysis technique of AD-PROM on real programs with many test cases and call sequences. The required call sequences that we needed to train to the model were collected by running the test cases that were provided with the datasets. We considered these sequences as normal sequences. We also created real payloads and synthetic anomalous sequences to test the system. In the first experiment, we compared AD-BROM with C-Markov, as C-Markov is the closest to our system, The goal of this experiment is to evaluate the system accuracy at detecting real attacks that aim at leaking data. We created 5 attacks. The first 3 attacks, we assume the attacker has access to the source code. In the first and the third attacks, the changes to the code issue call sequences similar to other branches in the program. In the fourth attack, the attacker has access to the binaries. We use instrumentation tool to rewrite the binaries and insert commands to redirect data to a file. In the last attack, we assume the attacker doesn't have access to neither the source code nor the binary, and there was a vulnerability in one of the applications. So the attacker performed an SQL injection attack to retrieve all the records from a table. We can see from the results that C-Markov was not able to detect attacks 1 and 3 or recognize if the activities were performed on data from the database. Finding the data dependency and recording the blocks IDs enabled AD-BROM to detect all the attacks. In terms of time performance in calls collection, C-Markov uses ltrace to collect library calls and the instruction pointers. It then uses address to line to translate the pointers to the caller functions. In our system, we built our own collector using an instrumentation tool. The collector collects both the calls and the callers while the program is running. On the average, AD-BROM's collector decreases about 78% of the overhead that ltrace introduces. We generated 3 types of anomalous sequences, one by replacing part of a normal sequence and adding random calls from set of legitimate calls. The other type, we add new calls. And then the third type, we increase the frequency of some of the legitimate calls. We compared the performance of AD-BROM and the regular hidden Markov model that initializes the model randomly. We evaluated the ability of both models to recognize new sequences, including the first anomalous sequences and the normal sequences. We can see from the curves that AD-BROM outperforms the random hidden Markov model in all cases. We evaluated also AD-BROM's ability to detect the second and third types of anomalous sequences. We computed the confusion matrix of each application model. Overall, the system performed very well at detecting the anomalous sequences with an average accuracy of 0.99. In future work, we plan to consider web applications, as we currently only worked with desktop applications. We also plan to provide full detection system that works at all data states by integrating our system with other systems that detect anomalous actions at other data states. We also plan to enrich the profiles and enable the system to detect more attacks by collecting more data about the executed queries. The goal of our work is to sum up, the goal of our work is to design a system that is able to monitor the use of data by applications in order to detect indications of potential data leakage. We have designed, implemented, and experimentally evaluated AD-BROM. The results show that our system have very low false positive rates, and it's highly accurate at detecting changes in the application program's behaviors. Thank you so much to all of you for listening. Please, if you have any questions, let me know.
Please type any questions you have on the chat box. In the meantime, I'll go and ask one question. Darren, please unmute yourself to answer. So basically, it's not clear to me how, by looking at the control flow graph, you can capture SQL injection type attack. Basically, it won't change the control flow graph in most cases. It will only change the input parameters maybe. Like instead of having, let's say, SQL injection attack.
I understand.
So I'm not so sure how you can get detect the SQL injection attack by just control flow graph. Please go ahead.
Yeah, sure. I know that SQL injection attack usually they don't change the flow of the program, and we also in our system in the paper we mentioned that we only can detect SQL injection attacks that aim to exfiltrate data. So if the attacker could retrieve all the records and then the program print this data, then the print command will issue the program will issue the print command more than the usual rate, and it will issue a new call sequence. That's how we can detect this attack. In the paper we explained a detailed example. If you want, I can share the screen and show you the example from the paper.
I mean, if it's not too much, yeah, please do share and see how it will work.
Yeah, sure.
I think we have time. Because to me, the program control flow is not changing. And if you don't have, maybe you can, yeah, go ahead.
I'm sorry, yeah, I cannot because, yes, let me try now.
Yeah, sharing may be an issue. I'll take a look at the, okay, you are now, yeah, you can share your screen now, yeah.
Can you see now the example?
Yeah.
Yeah,
yes.
So before the SQL injection, this query will retrieve one record from the database, right? And then it will print this record. So this is the normal call sequence. The user injected, the attacker injected a malicious value. It will retrieve more data, and then the program will issue more print command, and this is abnormal sequence, and we can detect this.
Okay. So basically, you have to count the number of times it's been called. So if there is a varying number of, assume this selectivity changes, like sometimes it retrieves 3 records, sometimes 12 records. So you have to somehow learn.
And we mentioned also in the paper in the limitation that if the attacker, if the SQL injection attack had the same selectivity like the original query, then we cannot detect that attack.
Okay. Let me ask the Tamir's questions. How he or she has to, how to deal with application legitimate updates such as new versions. So what happens if the update? So what happens with the update? So do you need to rebuild the sequences?
You mean we have to rebuild the model?
No, I mean, so what happens if there is an update to the program? So the call flow.
We should rebuild that because we have to know the changes to the control flow.
And the second question Tamir asked is how to deal with applications using ODBC.
I'm sorry, I couldn't hear you.
How to deal with applications using ODBC.
We usually have indicative instructions. We collect, a list of these. For example, ODBC, they will have specific functions to execute queries. Then we will label these instructions, and also it's just a library call that we have to add to the list that we monitor during the data analysis and the control flow analysis.
Okay, are there any other questions? Tamir said thank you. If not, let's thank the speaker again. I'm sorry, virtual thank. So we'll go to the, thanks, Saren. We'll go to the last, actually Shad has a question, let me ask. Shad wanted to ask how the static dynamic flow analysis difference in database application setting versus, say, for example, in the context of mobile applications studied in systems community. So in other words, are there any differences in the dynamic static analysis that you use for database applications versus regular mobile applications? Because I think what Sharat is, Sharat, you can unmute yourself and I think ask the question. I think.
Hi. Yes. Can you hear me?
Yes.
Yeah. So I guess Murat asked the question. So nice talk. But I wanted to just curious. Are there something special that sort of shows up in, except for SQL injection attacks, I guess, which is sort of there, but anything special that is here as compared to, let's say, NSDI, what people study in the mobile community?
Currently, we didn't study this part, the mobile application, but we're planning to do that in the future work. And we will try to understand the differences between the desktop application and the mobile application to know if the system will work with the different behavior of the mobile applications.
I think the question was more like, what's preventing you to apply? Forget about database aspect of this.
Mm-hmm.
And there's also work in the software security world that tries to analyze the programs, like static analysis, dynamic analysis. So what would be the difference of in this domain? So is it like, can you just take this and it would be working in the traditional software security world?
Yeah, I think well, that's what CMarkup does. They don't do the data flow analysis, so they cannot detect the data, what happens to the data, but they can detect changes to these applications. So without the data analysis, you can use it with other applications.
Mm-hmm. So I think, Sharat, my understanding is that, Darren, correct me if I'm wrong,
Hello.
You get the data, based on this data, you can simulate the sequences, therefore, based on the underlying database, so you can create a better.
Can you repeat?
Huh?
Can you repeat?
Sure. So my understanding is that by looking at the underlying database, you can generate sequences in the control flow graph and learn a better control. Hello?
Hello?
Connection is bad, I guess. Let me mute myself. Maybe that might be because of the problem.
I'm not so sure it's the case. Darren, anyway, we'll take.
No, I couldn't hear you. There was a glitch. I couldn't hear.
Sure. Can you hear me now?
Yes.
Okay. So I think the discussion was that in your work, by looking at the underlying database, you can generate control flow graph sequences. So access to data give you more information about how control flow graph works in practice.
Oh, and I think that get learned in the model that she learns.
Yes, that's
okay. Got it. That's interesting. Yeah.
Okay. Darren, so if you couldn't hear us, I think we agreed on something, but hopefully. By the way, I wanted to emphasize that there is a Slack channel associated with this session. So I would encourage everyone after this thing to hopefully continue discussions. So let's get advantage of the Slack later on to continue and any follow-up questions that you may think. So authors, please follow the Slack channel and register for that after the session. So let's go to the last talk of the session, which is SFour, a protocol for cryptographically secure record linkage at scale. It would be, sorry, what happens is that when I'm by Basit Kuram, again, sorry for butchering the names. Basit is a recent master's graduate from the University of Waterloo. During his time there, his research focused on the open problem of private record linkage. So let's go to the last talk. Please, Parnav, play the talk.
Hello, my name is Basit. I will be presenting to you a joint work between Encryption and myself, SFour, a protocol for cryptographically secure record linkage at scale. It is my hope that by the end of this talk that you will have an understanding of the meaning behind this title. In order to advance medical research, it is essential that health practitioners collaborate with one another, especially during times of crises. However, the exchange of information between health institutions is strictly regulated, and understandably so. This brings us to our topic of discussion, private record linkage. The act of finding records across multiple datasets that refer to the same entity while minimizing data leakage across different data owners. As most things, there are trade-offs involved in solutions to this problem. Here we deal with trade-offs in terms of the accuracy, efficiency, and security of solutions. Our goal is to produce a protocol which offers a guarantee of cryptographic security, runs with high accuracy, and executes in self-quadratic runtime. To our knowledge, our protocol is the first to accomplish all three criteria. We first present an example solution known as the all-pairwise comparisons approach. Here, we have two datasets, each belonging to different owners. The protocol proceeds by performing a secure comparison of each record in one dataset with each record in the other dataset. These secure computations is cryptography to allow comparisons without revealing the records themselves. While this approach is secure, it runs in quadratic time. Another solution involves the idea of hashing records into different bins so that similar records may end up in the same bins. After the records are hashed, pairwise comparisons can be performed within the bins. While this approach may run in sub-quadratic time, it turns out that having differently sized bins can leak information about the datasets. There are also approaches that make use of trusted third parties. However, we generally do not believe in the practicality of having access to a truly trusted third party. To offer a quick overview of background knowledge, a protocol makes use of what are known as secure multi-party computations. These allow computation on jointly provided inputs without revealing anything about the inputs, except their sizes and any information that might be inferred from the outputs. A common example is that of the Bilinears problem, which asks to determine the wealthier of two individuals without taking either's net worth. On a further note, it is possible to use logical circuits to execute secure multi-party computations. This means that you can compute a lot of things securely. With that said, here's a breakdown of the primary pieces of a protocol. There are 4 steps in SFour, and in order they are the sorting step, the scoring step, the sliding window step, and the shuffling step. I will go over each of these in more detail in the upcoming slides. But first, we need to have a discussion on the initialization process. Both parties need to agree on the total number of records that they will be processing. They need to agree on a common scoring function, and they need to append some identifiers to the records. Perfect. Step 1, the scoring step. The protocol participants have a common function that they use to score their records. The scoring function takes in a record and outputs a numerical score for that record. The scoring function works such that 2 records that are similar to one another have scores that are also close to each other. Here we have 2 datasets. Note that each dataset contains a zone. The one on the right has an umlaut on the E, but the 2 records are exactly the same otherwise. These 2 records are similar to one another, and so they have similar scores as one another. In the first step, the data owners score each of their records privately, that is, they do not share the scores of their records. Step 2, the sorting step. This step has 2 parts. First, each data owner individually sorts its records by score. Without going into the details here, the rest of the protocol requires the participants to share cryptographic representations of their records with one another. This secretive sharing allows the 2 parties to compute functions on each other's records without being able to see the records in plain text. After the participants sort their individual records, they invoke a secure computation and use a merge network to obtain a list containing sorted representations of their records. As of now, the fastest merge network runs in n-log n time. To emphasize, the participants are unable to see the records in plain text. However, the slide here shows what the records would look like were they able to see the plain text. Step 3, the sliding window. You may have begun to see where this is going. In the previous step, we were able to bring similar records close to one another. In this step, we'll pass a sliding window over the sorted records. As the sliding window passes the records, each record that is in the window at any time is compared with every other record also in the window at the same time. Recall that we are still in a secure computation, so these are secure comparisons. After the window is passed over all the records, we might be able to see something like this, a Boolean indicating which records are matching records. However, we cannot get under secure computation. If the participants were able to see the sorted ordering of records, they could infer information about records with the datasets. For example, with the Zoe record at the bottom, a participant may be able to infer that the other participant has records with scores lower than 416. Depending on the scoring function, this could leak the presence or the absence of certain records in the other party's dataset. This brings us to step 4, the shuffling step. Before we complete a secure computation to amend the protocol, we must shuffle our current results to prevent this leakage of positional information. Unfortunately, shuffling a secure multi-party computation is a slow process. One of our contributions in this paper is a new oblivious permutation technique which allows us to privately permute these records. I apologize if this part becomes a little repetitive, but this is a slightly involved trick, and any repetition is done at least slightly for my own benefit. Let's remember that our protocol participants appended some identifier tags to the records during the initialization step, the so-called step 0. Each of these tags looks like this. A concatenation of an owner bit, this being a bit indicating which owner owns this record, a 1 for party 1, a 0 for party 2, for example, a match ID, this to help indicate that the attached record is a match, a mismatch ID, this to help indicate that the attached record is not a match, and another ID, this to act as a sort of dummy identifier and actually indicate no information about the attached record. At the end of the protocol, each participant will receive a list of identifiers that is specific to that participant. The match ID and mismatch ID attached to a record are generated privately by that record's owner. The other ID that is attached to a record is privately generated by the other party. The record owner does not know the value of the other ID attached to its own record. These identifiers are all randomly generated. The choice of identifier picked for a record will depend on who owns the record and on whether the record has a matching record belonging to the other participant. To help illustrate how these identifiers work, we're going to go back to step 3 of the protocol. Near the end of step 3, this is what the results of comparisons look like. What we want instead is something like this. Here the records are color-coded to indicate which record belongs to which owner. I apologize if you have difficulty distinguishing the colors from one another, but when I say red, I'm referring to the color used for the record on the top. When I say blue, I'm referring to the color used for the record at the bottom. The identifiers on the right are blue, because these are the identifiers that will be given to the blue party. Remember, each participant receives its own list of identifiers. Okay, so each of the records has an order bit, which indicates which party owns the record. Each record also has attached to it a match ID, a mismatch ID, and another ID identifier. Recall, only the record owner knows the values of the match ID and mismatch ID attached to the record. Also, the value of the other ID attached to the record is not known by the record owner. During the secure conversions in step 3, we see that the first record on the top has no matching records. For this record, the protocol selects the mismatch ID. The blue party will eventually see this identifier in plain text. However, since the record belongs to the red party, the blue party will be unable to get any meaning from the identifier. That is, the blue party will be unable to determine that this is a mismatch ID. Since the red party generated the identifier and the blue party does not know how to categorize identifiers generated by the red party. Going on to the second record, we have the same thing as before. Here is a record with no matches. It belongs to the red party, so we picked the mismatch ID. The third record is different. This record belongs to the blue party. Here, we pick the other ID that is attached to this record. Record owners do not know the values of the other ID identifiers that are attached to their records. So, when the blue party sees the other ID attached to its record, it will be unable to determine to which class of identifiers this identifier belongs. The red party generated the identifier, and just as with the previous identifiers generated by the red party, as far as the blue party knows, this identifier could be match ID, a mismatch ID, or another ID. And again, with the fourth record, we see the same thing. This is a record belonging to the blue party. We select the other ID. When the blue party sees this identifier in plain text, it will offer no information to the blue party. The fifth record belongs to the red party. This record has a matching record. Here, we pick the match ID attached to this record. Again, the match ID was generated by the red party, and so the blue party is unable to gain any information from this identifier. And finally, we reach the last record. This is a record that belongs to the blue party. Like with other records that belong to the blue party, we pick the other ID that's attached to this record. Again, the other ID is generated by the other party, and the blue party is unable to gain any meaning from this identifier. The blue party now has a list of identifiers. All these identifiers were generated by the red party and provide no information to the blue party. And so it would be safe for the blue party to see these identifiers in plain text. Similarly, the same process can be followed to generate a list of identifiers for the red party. Now, both parties have identifiers that mean nothing to their respective selves. At this point, we are ready to enter secure computation. For the two parties to exchange their lists of identifiers, we will be able to learn the results of the matches. But we still need to shuffle the identifiers. Each party can shuffle the identifiers in its list. The identifiers are in plain text. There is no cryptography required here, so this is a fairly quick process. The parties then exchange the list of identifiers. Now, each party possesses a list of identifiers that it generated. The parties can categorize the identifiers by type of identifier and learn which other records have matching records from the received match ID identifiers. Here are the shuffled plaintext identifiers that the blue party received from the red party. The blue party sees that the first identifier from the top is a match ID. The blue party generated this identifier and can check its internal mapping of identifiers to check which record is associated with this match ID. The second identifier is a mismatch ID. The blue party can determine which record had this identifier and determine that that record does not have a matching record. The third identifier is another ID that the blue party generated to attach to a record belonging to the other party. This identifier offers no additional information to the blue party and can be ignored. The blue party continues this process with remaining identifiers. The red party may follow the same procedure for its own identifiers, and with that, the SFour protocol reaches completion. As for the complexity of the protocol, The first step involves scoring individual records. Scoring the record takes constant time, and so the first step runs linear number of records. The second step involved the use of the merge network, and so this step runs an n log n time. The third step involved comparing records within a sliding window. The complexity of this step depends on the window size. A window size is log n, and so this step runs an n log n time. The final step was the shuffling of the plain text identifiers. This step runs in linear time. And so the overall complexity of our protocol is n log n time. This achieves our goal of having a subquadratic runtime. For the security analysis, we make use of Goldreich's composition theorem, which states that a protocol securely composed of secure subprotocols is itself also secure. The first step of our protocol involved the parties locally scoring the records. There is no communication here, and so this step is secure. The second step is executed in a secure multi-party computation, so this step is secure. The third step continued the secure computation from the previous step. The secure computation ended with each party having random identifiers that only made sense to the other party, so this step too is secure. The fourth step is a simple permutation and is also secure. The individual steps of our protocol are secure, and so by Goldreich's theorem, the overall protocol is secure. We implemented a protocol to run performance experiments. We used Ripple, a supercomputer cluster at the University of Waterloo, and limited each party to a single CPU and 108 GB of RAM. Our performance experiments used public travel data from the New York City Taxi and Limousine Commission. We had 2 parties, and each had a data set of around 4,000 records. The overall online runtime of the protocol is 77 minutes. This may seem like a lot, but the solution that came closest to accomplishing accuracy, efficiency, and security goals took around 80 hours to complete running on similar data sets. So we achieved an improvement of around 1 to 2 orders of magnitude. And then there's the all-pairwise convergence approach that I mentioned at the beginning. The approach that runs at quadratic time. This approach will take around 3 weeks to complete the same task. Here we have a graph of the results. On the y-axis, we have the time taken to complete the protocol. On the x-axis, we have the number of records in the data sets. There are 2 lines here because we experimented to see what happens if we choose the window size. Our experimental results confirmed our theoretical prediction of an n log n runtime with a window size set at log n. We ran some accuracy experiments too. OpenStreetMap and Yelp both have information about restaurants. Our OSM dataset had around 100,000 records, and our Yelp dataset had around 240,000 records. The datasets had around a 29% overlap. The records were in the form of geo-coordinates, and so we were working with numerical data. Our protocol was able to find around 97% of the matches in a single iteration. We confirmed 2 ways to increase our protocol's accuracy. After running the protocol, matches can be removed from the datasets, and subsequent iterations can run to find additional matches. Increasing the window size used in the comparison step also increases the protocol's accuracy. In this graph, the y-axis shows the percentage of matches that are found, and the x-axis shows the iterations that are completed. By combining both approaches, we were able to obtain around 100% accuracy of these datasets in just 3 iterations. We ran experiments using bibliographical data. The British National Bibliography dataset contained around 3 million records, and the Toronto Public Library dataset contained around 1 million. There's an overlap of around 70%. The records here contain strings. Strings are to be harder to compare than our numbers, so we expected low accuracy here. We obtained 85% to 90% accuracy in the datasets. And here's a graph similar to the one from before. We ran in some more experiments with the datasets containing strings. We ran experiments using the North Carolina voter registry from 2014 and compared them with the records from the one from 2017. Each had around 10 million to 11 million records with around a 93% overlap. We obtained around 98% accuracy in the first iteration. And here's another graph. Overall, we were pretty satisfied that the SFour protocol achieved relatively high accuracy rates. With that, we have reached the final slide of this presentation. SFour, a protocol for cryptographically secure record linkage at scale. It is my hope that that title makes more sense to you now than it did 15 minutes ago. Thank you.
Thanks, Basit. Wendy asked, can you briefly explain the scoring function in step 1? Is it independent of similarity metric used for record linkage? Basit, you can unmute yourself.
Yep. So the paper goes into detail about techniques that we use for ideas of like scoring functions like PNF. The one that we use in the paper is a Hilbert function, which
can you repeat again?
A Hilbert function.
I don't know what this is.
It ends up being like it's sort of like a mathematical projection that allows you to like reduce the number of dimensions that you have. So I can pass in an array integers, let's say, and that would reduce it into a single dimension. And the idea being that if points in space are close to each other, then their Hilbert scores will also be close to each other.
The second question was, is it independent of the similarity metric used for the code linkage? So did you do an exact equality matching, or you do a similarity matching?
We do similarity matching.
What's the similarity function used on the records when they are matching?
Right.
For example, for text, they can use edit distance, for example. So does the similarity metric used on the record linkage needs to be compliant with this embedding, I guess, right? Or whatever you call the output function.
Yep. With similarity metrics, you end up doing pairwise comparisons with every single thing. That doesn't work with our procedure. What we do is we pass in a single record and we get a single score for that record. So we don't perform any similarity metrics between two records. We are projecting all of our multi-dimensional records into a single dimension, and then we're sorting them, and then just comparing similar records.
The reason I think Wendy has asked, Wendy, correct me, because in many cases you would have different way of mapping things. Like, for example, you talked about North Carolina data set. There may be typos in the names, for example. And because of these typos, you may want to have some kind of certain similarity matching for typos instead of non-error versions. I guess that's the reason the similarity metric could be an important thing.
Yes, the Hilbert functions or the Hilbert projections account for those errors. So if a name is off by a few characters, if we try and project that name into like some n-dimensional space, the names would also be very close to one another in that space. And so when we project them into a single dimension, they will also be close to each other. So that is how we are accounting or attempting to account for errors or typographical issues that may arise in records.
Mm-hmm. So in your experiments, did you try with errors, or there were no errors?
So we had some synthetic experiments that we ran, which I did not mention here. Those performed really well. The data sets that I mentioned here were all like real data, and they included errors. We did not really do any cleaning of them, apart from like some simple parsing. But yeah, most of these real data sets would contain errors.
Not necessarily. North Carolina data set had errors, but if you join it by itself, it depends how you set up the errors. So there are some synthetic, you have to generate your errors yourself to have a record thing. Anyway, we can take it offline. So there was another question. Ninging asked, thanks for the nice talk. In shuffling without the cryptographic scheme, whether the attackers can link two records that belonging to the same type or reveal other information. So I think Ningling's question is like the shuffling, does it leak anything?
I'm trying to understand the question again, sorry.
Ningling, can you unmute yourself and ask the question maybe?
Yeah, I think in the shuffling without the cryptographic scheme, the attacker may get some other information about the privacy. Can you explain about that?
No, we aren't aware of any information that might be leaking. In fact, we assert that there is no information that can be leaked during that process. The identifiers that we are using are all random strings. And when the parties are shuffling them, like no one can gain any information of the identifiers except for like the owners of the identifiers. We're assuming, of course, that the two parties can communicate with one another over a secure channel so that no one else steals the identifiers during transit.
Yeah, maybe the records have the same type. They can have the same the ID you transformed. So attacker may link the two records.
The identifiers are independent across the two parties. Like the red party's identifiers are like have no correlation with the identifiers used by the blue party.
Yeah. Yeah, okay, okay. Thank you. Thank you very much.
Shantun has a question about slide 51. Shantun, unmute yourself. And
Hi.
Florian has a comment later on. We'll let Florian to unmute as well. Shantun, go ahead. Unmute yourself and ask the question.
Hi, thanks for the talk. And I want to ask you in slide 51. So the meaning of the window size that you are comparing means every time you are comparing log n to the power 2, the size of the window. The notation that you used in your figure, window size log n, this is square 1.0. What is the meaning of this?
Right. So for the 2.0, that notation over there is just like log of n times log of n. We use different window sizes. The graph over there with the orange line over there is when we have a window of size log n squared. The blue one is our standard window, which has a size of log n, just log n to the power of 1.
Okay. Thank you.
Florian had a comment saying that we use different years of NCVR, so it does have natural errors. My point was slightly different in the sense, even if there are natural errors by adding new people, if you link across different data sets, for example, Bill can be registered as William, etc. So therefore, the errors can be quite different than what the different versions of NCVR. But I guess that's a separate discussion we can have on the Slack. So Slack is very useful for this kind of follow-up discussions. So are there any other questions? If there are no further questions, I'm looking at chat window one more time. As I mentioned, please continue the discussion on Slack and please follow it after the talk. Thank you so much for all the presenters and all the lively discussion via chat and so on. Florian has further comments which will follow. He's saying that this works in CVR. The type of errors I mentioned exist in CVR. So I will take a look at it, Florian. Thanks for your comment. And we will talk, the sessions will start tomorrow at 7:30 with Alibaba. Yeah, so we will please continue with Slack. Thank you all for joining the session and hope please continue attending the ICD. Thanks. So we are now closing this, the first security and privacy session. Bye.